Welcome to Chemistry with Dr. Z. In this video, I will be talking about halogen alkanes or haloalkanes or alkyl halides. I'm going to talk about their substitution and elimination reactions and also their physical properties. So let's start off by talking about the structure of alkyl halides. So what are alkyl halides? Alkyl halides or halogen alkanes are organic molecules that contains a halogen atom attached to a carbon atom. And based on the structure or where we can find the halide or the halogen in the carbon chain, we have three types of alkyl halides. The first one is the primary halides or the primary halogen alkanes. These ones have the halide attached to a carbon that has two hydrogens attached to it. An example of that is ethyl chloride, so CH3, CH2Cl. So the chloride is attached to this carbon which has two hydrogens. And then we have the secondary halides where we have the halides attached to a carbon that only has one hydrogen attached to it. An example to this, we can find the 2-propyl chloride, so CH3, CH3, and then we have the chloride, so this is a secondary alkyl halide. And then finally we have the tertiary alkyl halides where the halogen is attached to a carbon that has that has no hydrogen attached to it. So if you have a carbon like this with three alkyl group or three methyl groups like this, and then it has the chloride here. So this is 2-chloro, 2-methyl, 2-propanol, propane. This is the tertiary alkyl halides or tertiary halogen alkane. So physical properties of alkyl halides or halogen alkanes. So alkyl halides are polar compounds. The main reason for that is due to the asymmetric distribution of the electrons in the bond between the carbon and the halide. This is due to the difference in the electronegativity between the halide and the carbon. So this creates a dipole moment that is responsible for the polarity of these compounds. So if we have something like methyl chloromethane, there is the chloride is more electronegative than the carbon, and that means that the chloride has more tendency to attract the electrons in the bond between them. So there is a dipole moment where electrons are more toward the chloride than the carbon, and that creates a partial positive charge on the carbon and a partial negative charge on the halide. And this change or this polarity affects both the physical properties of alkyl halides and also their chemical properties or their reactions. So let's look at the effect of polarity on the intermolecular attraction or the physical properties. So these are polar compounds because of the presence of the dipole moment. So there is a permanent dipole moment and there is a dipole-dipole interaction as we can see here. So if we have a dipole moment here, a partial positive charge on the carbon, a partial negative charge on the fluoride as a halide, and then here on the other side, the other compound, we also going to have a partial positive on the carbon and a partial negative on the fluoride, and there will be a dipole-dipole interaction between the partially positive and the partially negative atoms on the two different molecules. That creates a dipole-dipole interaction, and this is stronger than the van der Waals interaction that we have found before in alkanes. Because this is why haloalkanes or halogen alkanes have higher boiling points compared to the alkanes. Compared to alkanes, they have higher boiling points and melting points. So the intermolecular forces will affect the boiling points. Within the same series of compounds, for example, for different alkyl halides, the boiling point will increase as the molecular weight increases. The main reason for that, we have more of the van der Waals forces. If the chain of the carbon increase in size, then you have more atoms, and then you have more of the van der Waals interaction between these atoms, and that will increase the boiling points and the melting points. However, down the halogen series, the boiling points also will increase. So iodides have higher boiling points than bromides, which will have higher than chloride, and so on. And this is because of the increased polarizability down the group. So if you look at this table, for example, if we compare the different methyl halides, so you're going to find the fluoride has lower boiling point than chloride, than methyl chloride, than bromide and iodide. And this is constant for the different alkyl group. Chemistry of the alkyl halide. There are two types of reactions that alkyl halides or halogen alkanes can undergo, and this is due to the polarizability of the nature of the bond between the carbon and the chloride and the halogen or the halide. The first reaction is called the nucleophilic substitution reaction. So they undergo nucleophilic substitution with a nucleophile. So in this reaction, we have a nucleophile, and a nucleophile is any atom or group of atoms that could either have lone pair of electrons or a negative charge, and they can donate this electrons or a negative charge to a carbon atom that is deficient in electrons or deficient in a charge. So for haloalkane or halogen alkanes, we know that this bond, the carbon will have a partial positive charge. So the nucleophile can actually give its electrons to this carbon atom, and that leads to the breaking to the breaking of the bond between the carbon and the halide, and then the nucleophile will substitute the halide. So now we're going to have a new product, and the product will depend on the nature of the nucleophile, and the halide will leave as a negatively charged halide. The second reaction is the elimination reaction, and they undergo elimination reaction with bases. So an example of that, if you have a base, and then we have the alkyl halide. The alkyl halide, when we have two carbon atoms attached to each other, with one of them having the halide and the other one has a hydrogen, then the base can actually take the hydrogen, and then the halide will leave, while this electrons between the carbon and the hydrogen will make a double bond between the two carbons. So that will lead to formation of a new double bond, and the product will be an alkene, and then the halide will leave with the hydrogen, and or the base will react with the hydrogen, and the halide will leave in this reaction because it's a leaving group. So let's have a closer look at the mechanism of these two reactions with the specific examples. So let's start off with the nucleophilic substitution reaction. Nucleophilic substitution reaction, we can also, always denote it by the movement of the electrons. We use the curly arrows here in any mechanism of the reaction to assign or to denote the movement of the electrons, not the movement of groups or atoms. It's just we can just assign it for the movement or indicate the movement of electrons. So here we have a nucleophile. We have a nucleophile and we have a leaving group, which is the halide. The nucleophile first, which has a lone pair of electron, will attack the electron deficient carbon. And as we can see, the arrow will go from the nucleophile or from the electrons on the nucleophile towards the carbon. At the same time, the leaving group will start to leave. And as it leaves, now it breaks, the bond will break between the carbon and the halide, and as you can see, the arrow now goes from the bond towards the halide. And this is the new product, the substitution product, where the halide has left and has been substituted with the nucleophile. This is why this is called nucleophilic substitution reaction. You can actually have so many different examples, and in your exam they could give you any example, any nucleophile and a halogen alkane, and ask you to draw the product. So you simply look at the nucleophile, the one which has the one which has a negative charge or a lone pair of electron, and then you're gonna substitute the halides from the structure with this new nucleophile. So if you have hydroxide and then you have something like methyl chloride, you're gonna end up with methanol. If you have something like, even if you have another halide like iodide with alkyl bromide, you're going to end up with the alkyl iodide and the bromide will leave. And if you have a cyano group, then it will also, a cyanide, it will also react or substitute the halide, and that will give you a nitrile. So you just need to look at your different nucleophile that you are given, and then you can simply think of the product. So let's have a more specific examples now, look at the mechanism and also look at the conditions of the reaction. So the first reaction is reaction of halogen alkane with hydroxide. So if you have hydroxide and you have halogen alkane, the reaction can proceed via substitution, and that will give you the methanol, or will give you the alcohol. In this case, you need to heat the reaction using aqueous sodium or potassium hydroxide solution. This is very important, the use of aqueous sodium or potassium hydroxide solution. You don't use ethanolic solution, you use the aqueous sodium or potassium hydroxide solution. The mechanism is very easy, where you have the lone pair of electrons on the oxygen will attack the carbon, while the bond between the carbon and chloride will go towards the chloride and the bond will break. That will give you the product, the substitution product with the OH, and then the chloride ion will leave. The second reaction is reaction with cyanide. So the reaction with cyanide proceeds in the same way, the same mechanism. So you have the cyanide ion, which has lone pair of electron, has a negative charge. It will also attack the attack the carbon, which is electron deficient, the one with the partial positive charge, while the bond between the carbon and the bromide will break and the electrons will move towards the bromide. In this reaction, the reaction condition, you need to reflux using ethanolic solution of sodium or potassium cyanide. And then the product will be nitrile, so we simply substituted the bromide with the cyanide to give you the nitrile. The third reaction is the reaction with ammonia. Reaction with ammonia is a bit different because there is an extra step in this reaction. So you can see that ammonia doesn't have a negative charge, but it has lone pair of electrons, so still can act as a nucleophile. So the ammonia will attack the first step, the lone pair of electrons will attack the electron deficient carbon, or the carbon with the partial positive charge, while as all the nucleophilic substitution reaction, the bond between the carbon and bromide will break. And then the next step, now the new bond that has been formed, as you can see, between the carbon and the ammonia, the nitrogen will have four different atoms attached to it, or will have four different bonds. That means that the nitrogen will have a positive charge. So the nitrogen now has more than it can carry, and it will have a positive charge. In this case, the extra hydrogen on the nitrogen will leave because there is an extra ammonia in the reaction mixture. So the ammonia now, the extra ammonia in the reaction mixture will act as a base, and it will attack the extra hydrogen. So the mechanism here is that the lone pair of electrons on the nitrogen as a base will attack the hydrogen, while the bond between the nitrogen and the hydrogen will break, and these electrons will go to the nitrogen. Now the nitrogen will not be positively charged, and with that will give you the final product without any charge, which is the ethylamine in this case, and we're going to have the ammonium ion. The ammonium ion, along with the bromide that left as the in the first stage, or in the first step, as a leaving group in the substitution reaction, can then be bonded together to give you ammonium bromide. The condition for this reaction is to heat the reaction in a sealed tube using ethanolic ammonium solution, or ammonia solution. The rate of the reaction will depend on the strength of the bond between the carbon and the halide. What do we mean by this? The strength of the bond between carbon and halide will determine the reactivity of the substitution reaction. So if we look at the enthalpy, the bond enthalpy for different alkyl or carbon halogen bonds, you're going to see that carbon fluoride has the strongest because it has the higher value for bond enthalpy. And that means that the carbon fluoride bond is harder or more difficult to break, which means that it will react more slowly compared to the other alkyl halides. And carbon iodide, or carbon with the bond between carbon and iodine, has the lowest enthalpy, which means it's the weakest bond. So the any alkyl iodide will react faster than the other halides. So as we go down in here in the periodic table, you're going to find that there is a faster substitution reaction. So we can look at the different leaving group and we can have a trend now along the periodic table. So along a column of a periodic table, we're going to have better leaving group as we go down. So halides as leaving group, you're going to have the iodide as the best one, followed by bromide, followed by chloride, followed by the fluoride. And although fluoride is the most electronegative of all of these, but the iodide, which is lower in the periodic table, it's more polarizable and it's actually weaker. This is because of the size of the atom. Because of the size of the iodide atom, which have its electron in the 4p orbital, that means, or electron shell in the 4p electron shell, that means that the electrons in the outer shell, or the electrons that are bonded with the carbon, or that is bonded or are used in bonding, is further away and more shielded from the nucleus, the positively charged nucleus. So that means that it's more polarizable, it's more easily broken compared to the carbon and fluoride bond. So it's a better leaving group. So we decided and we know now that reactivity will be related to the strength of the carbon halide bond. The other type of reaction is the elimination reaction. In these reactions, the nucleophile that we have been using before will act now as a base, not as a nucleophile. So the mechanism of the reaction is also very simple. So we have the base now, the nucleophile, we're going to call it base, and the B here refers to the base. The base will attack the hydrogen on the carbon adjacent to the carbon that has the halide. And again, we use the curly arrow to indicate the movement of the electrons, not the movement of the group. So the electrons on the base will attack this hydrogen, and that means that the bond between the hydrogen and the carbon will break, and this bond will actually go between the two adjacent carbon. At the same time, the bond between the carbon and the bromide will break, and the bromide or the halide will take these electrons. That leads to a formation of a new double bond, as we can see here. So the product of the elimination reaction will be the alkene. A specific example of elimination reaction is reaction with hydroxide ion. The hydroxide in this reaction will act as a base, will not act as a nucleophile as before. So as we can see in this reaction, we have the hydroxide ion, and this is the exact same mechanism. The hydroxide attack the hydrogen carbon bond break to make the double bond, and that allows for the leaving group to leave as well at the same time, making the new bond, which is the alkene. You may wonder why the hydroxide reacted differently this time, because we have seen that the hydroxide can react with alkyl halides or with halogen alkanes to give the substitution reaction product, which is the hydroxide. In this case, or the alcohols. In this case, it has reacted differently, and this is because of the different reaction condition. So, if you want the reaction to proceed via elimination, not substitution, you need to heat using ethanolic potassium hydroxide or sodium hydroxide. So you don't use aqueous sodium or potassium hydroxide, you use ethanolic potassium or sodium hydroxide. If you use aqueous sodium or potassium hydroxide, the reaction will proceed via nucleophilic substitution.